This is the EdExcel Advanced Extension Award in Maths, and it's from the sample papers. Now this is a non-calculator paper. Question number 1. For part A, for the absolute value of y being less than 1, we have to write down the binomial series expansion of 1 minus y to the power of minus 2 in ascending powers of y up to and including the term in y cubed. For part A, we have 1 minus y to the power of minus 2, which is equal to, well, the first term will be 1, the second term will be minus 2 multiplied by minus y divided by 1 factorial. The next term, we've got minus 2 multiplied by minus 3 multiplied by minus y squared divided by 2 factorial. For the next term, we've got minus 2 multiplied by minus 3 multiplied by minus 4 multiplied by minus y to the power of 3. And then we divide this by 3 factorial. And then we've got higher order terms. And if we simplify all of this, we've got 1 plus 2y plus 3y squared plus 4y cubed, so on and so forth. For part B, we have to show that when it is convergent, the series 1 plus 2x over x plus 3 plus 3x squared over x plus 3 all squared, so on and so forth, can be written in the form 1 plus ax to the power of n, where a and n are constants to be found. Now, we've got our series S over here, and we can rewrite S as 1 plus 2 multiplied by x over x plus 3 plus 3 multiplied by x over x plus 3 squared plus 4 lots of x over x plus 3 to the power of 3, so on and so forth. Now, let's compare with the result which we found here. We've got 1 plus 2y, well here we've got 2 lots of x over x plus 3. Here we've got a 3y squared, but here we've got 3 lots of x over x plus 3 squared, and so on and so forth. So, if we compare S with what we have in part A, we can therefore conclude that y is equal to x over x plus 3. And knowing what y is, we can use our result in part A to find out what S is, and we can write it in the form over here. We know that y is x over x plus 3, and so therefore using our result to part A, we have S equals 1 minus x over x plus 3 to the power of minus 2. And now we need to simplify s. So, combining the 1 with the fraction here, this result is the same as x plus 3 minus x over x plus 3. We are raising this to minus 2. And so x plus 3 minus x is just 3. And then on the bottom we've got the x plus 3. We are raising this to the power of minus 2. Because we've got a negative power, we can rewrite what's in the bracket as x plus 3 over 3. The consequence of doing so, we'll have to raise this to the power of 2. And the result here is the same as 3 over 3 plus x over 3 to the power of 2. In other words, we can conclude s is equal to 1 plus 1/3 x squared. The value of a is 1, the value of b is 1/3. For part C of the question, we have to find the set of values of x for which the series in part B is convergent. Now, we know from part A that the absolute value of y is less than 1, and we already know what y is. That's x over x plus 3. And so therefore, for part C, we can see the series is convergent for the absolute value of x over x plus 3 being less than 1. We're replacing y with x over x plus 3, which is why we got this result. So now, if I multiply through by the mod of x plus 3, we are left with the absolute value of x being less than the absolute value of x plus 3. We can now find our critical values. We replace the inequality sign with an equal sign, so we have the absolute value of x equaling x plus 3 modded. And so x plus 3 is equal to plus minus x. And if I deal with the positive, x plus 3 equals x, well, this has no solutions. And if I deal with the negative, x plus 3 equals minus x, from which we can see x is equal to negative 3 over 2. And now if I draw a graph to show all this information, we've got y equals mod of x, y equals mod of x plus 3. They intersect only at x equals negative 3 over 2. And what we need to do is find out where the mod of x plus 3 is greater than the mod of x, and is greater than over here. So what we need to do is solve this inequality. Reading off the solution, we can see then that the series is convergent on x belonging to a set of real numbers where x is greater than negative 3 over 2. Question number 2. For part A, on separate diagrams, we have to sketch the curves with the following equations. On each sketch, you should label the exact coordinates of the points where the curve meets the coordinate axis. For the first part, we have to sketch the graph of y equals 8 plus 2x minus x squared. Now, first of all, we can find out where the graph crosses the x-axis and the y-axis. So if I set y equal to 0, I've got 0 equals 8 plus 2x minus x squared. So I've got 0 equals minus x plus 4 multiplied by x plus 2, from which we can conclude x is either equal to minus 2 or 4, and when x is 0, y is equal to 8. So it crosses the x-axis at minus 2, 4 and the y-axis at 8. So when I sketch the graph, I have something looking like this. Here we've got the graph of y equals 8 plus 2x minus x squared. And we know that it crosses the x-axis at 4 minus 2. And it crosses the y-axis at 8. Next, we have the graph of y equals 8 plus 2 multiplied by the mod of x minus x squared. So, for me to sketch that graph, if I mod x, that means for this portion of the graph, I need to reflect it in the y-axis, so I end up with something looking like this. And the reason for that is the negative values of x will give the same output for y as we have positive values of x. So you can see here the y coordinates are always the same for the positive and negative x values, which is why this part of the graph is reflected in the y-axis. So when I come to sketch that graph, I have something looking like this. Now here, as before, it crossed at the point 4. So this point will be negative 4 because we've reflected this part in the y-axis, and the y-intercept will remain at 8. And so here we have the graph of y equals 8 plus 2 multiplied by the mod of x minus x squared. And next, we have to sketch the graph of y equals 8 plus x plus the mod of x minus x squared. Now, here is where things get slightly more complicated. For the third part, we've got y equals 8 plus x plus the mod of x minus x squared. Now here, we need to see that for values of x being greater or equal to 0, rather, just values of x being greater than 0, what we'd have is y equals 8 plus 2x minus x squared. And the reason that's the case is because, say I have x equaling 3, then here I'd have 3 plus the absolute value of 3, so that's twice 3, which is why I get the 2 over here. But for values of x being less than or equal to 0, we will end up with the graph of y equals 8 minus x squared. Now, why is this the case? Well, suppose I have on the side, let's write it down, x equals minus 4. Okay? Then I have y equals 8 plus minus 4 plus the absolute value of minus 4 minus 4 squared. This bit over here is just 0. So if you want to think of it in terms of numbers, that might make it easier for you. But the idea here is to realize for values of x being less than or equal to 0, we've got the graph of y equals 8 minus x squared, and that's because the x plus the mod of x simplifies to 0. Now, if I was to sketch the graph of y equals 8 minus x squared, where x is less than or equal to 0, what you can see over here is when y equals 0, I have 0 equals 8 minus x squared, from which we can see x squared is equal to 8, and so therefore x is equal to plus minus 2 root 2, but we only take the negative, and the reason we take the negative is because x is less than or equal to 0. So when I come to sketch the graph, this bit of the graph from here to here, that's one bit of it, which is what we have here. But then for x being less than or equal to 0, I've got this graph to draw. It still passes through 8, but then the graph will look something like this. So let's sketch all of that together. We end up with this graph here. Still crosses at 8. Here, this part still crosses at 4. This part here crosses at negative 2 root 2. We have here the graph of y equals 8 plus x plus the mod of x minus x squared. For part B of the question, we have to find the values of x for which the absolute value of 8 plus x plus mod of x minus x squared equals 8 plus 2 times the mod of x minus x squared. Now, this graph, without the mod symbols, we've drawn in the third part of part A. We did that over here. And then the other part we drew over here. And what we need to do is mod this graph so these bits here will be reflected in the x-axis, and if I draw my original graph with it, then here is what we need to solve simultaneously. We've got y equals the absolute value of 8 plus x plus mod of x minus x squared, and here we've got y equals 8 plus 2 times the mod of x minus x squared. We need to find out where those graphs are equal. Now, they are equal clearly in between 0 and 4, and they are also equal at some point over here. So what we need to do is find out somehow what this point here is. So when we come to state the solution, first of all, the graphs are equal when in between 0 and 4, graphs are equal. So that's where this solution here comes from. But now we need to find the point over here. Now, this is where things get more complicated. It's quite difficult to spot how we find out the x-coordinate of the intersection between this graph and this graph. So let's go to Desmos. We've got this graph here, and we've got this graph here, which is what we need to solve simultaneously. Now, if I zoom out a little, how could we find those? Well, we've got this quadratic over here. We've got 8 plus 2 times the mod of x minus x squared. Now, if I show the original graph without the mod symbol, you can see how we've got the graph shown in red. But what happens if I was to continue with this graph in the positive x direction? What quadratic would I have? Well, in that case, I would have the quadratic 8 plus, rather, minus 2x minus x squared. And that's if I was to continue on with this quadratic here. And the reason that works is because of the symmetry of the graph about the turning point. And what you'd find is here, if here we had minus 4 and here we had 2, then 8 minus 2x minus x squared equals 0 will give a value of x equals minus 4 and a value of x equals 2. But how does that help us? Well, let's just get rid of that graph and let's get rid of this graph. We've got our graph over here, and if I mod it, I get that graph over here. I need to find out where this point is here. How could I do that? Well, what we mentioned is for this bit over here, we had the graph of 8 minus x squared. So let's just draw the graph of 8 minus x squared. And then if I draw this graph, you can see how between the minus 2 root 2 and 0, those graphs are equal. Now let's go back to this graph here. And let's mod it. Well, how could I find out the intersection point over here? Well, if I flip the graph over here by using a negative, and then if I draw this graph, you can see then how we find those intersection points. Because remember the effect of modding. The effect of modding a graph will just reflect it in the x-axis. And that's what this minus here does. The minus reflects the graph in the x-axis. And that's how we got that part and the other parts to equal. So if I draw my original graph, which is over here, if I was to reflect this part in the x-axis, we'd get this part over here. And then if I had the 8 minus x squared, shown here. And then hopefully you can see here with the original graph, I want to reflect that bit up. So reflecting that bit up gets that bit, and then multiplying this by -1 also reflects the graph. So you can see why we use the minus over here, because it reflects in the x-axis. So with that graphical explanation, you can see then what we need to solve is mod of 8 plus x plus mod of x minus x squared simultaneously with 8 plus 2 times the mod of x minus x squared. So how could we tidy this up even further? Well, this is the same as solving, as we've just shown, negative 8 minus x squared equaling 8 minus 2x minus x squared, with the restriction x is less than 0. So here I've got a graphical representation of what's going on. We've got the graph here of y equals negative 8 minus x squared, and here we've got the graph of y equals 8 minus 2x minus x squared. So with that graphical representation, what we need to do is solve this equation. So if I were to simplify the result here, perhaps if we move this to this side and then solve, we've got x squared minus 8 equals 8 minus 2x minus x squared, 2x squared plus 2x minus 16 equals 0. And if I divide by 2, we've got x squared plus x minus 8 equals 0. And using the quadratic formula, we've got x equals negative 1 plus minus b squared, so that's 1 squared minus 4 times 1 times negative 8. And this is square rooted. And then we divide by 2 lots of 1. And what we'd end up with then is x equals negative 1. Now here we need to take the negative, and that's because of the restriction x is less than 0. And then here we've got 32 plus 1, which is 33. And then we've got the 2 here, so we've got x equals minus 1 minus the square root of 33 over 2. And that's because x is less than 0. And therefore, when we come to state our solution, we've got x being in between 0 and 4. And we've also got the solution here, x equals minus 1 minus square root of 33 over 2. So these are the only solutions. Question number 3. Figure 1 shows a regular pentagon OABCD. The vectors P and Q are defined by P equals the vector OA and Q equals the vector OD respectively. Let K be the number such that DB is equal to KOA, and then we have to write down the vector AC in terms of P, Q and K as appropriate. Now here we've got a regular pentagon. What's essentially happening in this question, we've got DB, so starting at D, finishing at B. This is K times bigger than OA. So here we've got the vector K, P, where K is a constant. And what we need to find is the vector A, C. We need to find out what this vector is somehow. Now for us to do this, well, essentially the middle bit is bigger by a magnitude of K than the side opposite it. So if I think about AC, starting at A, finishing at C, the side opposite it is Q. And so this vector is K times bigger than Q. Because we've got a regular pentagon, this side will equal this side. So the vector AC is K times bigger than Q. And so here we've got the vector K, Q. So for part A, the vector AC is equal to the vector K, Q. And that's because we've got a regular pentagon. So for part B of the question, we have to show that CD, so starting at C, finishing at D, that's equal to minus P minus 1 over K, Q. Well, how could we start at C and finish at D? Well, we could go C to A, and then A to O, and then O to D. So, for part B of the question, we've got CD equaling CA plus AO plus OD. Now we know each of these vectors. We've got CA, the negative of this, which is negative KQ. We've got AO, which is negative P, and OD, which is Q. And that's shown in this diagram. And if I simplify this, we end up with minus P plus 1 minus K, Q. We'll call this 1. The problem is right now, this vector is not the vector we wanted to show. Fine, the minus P bit is the same, but here I've got a minus 1 over K, and here I've got 1 minus K. So at this point, what we can do is find out any other unknown vectors. So let's say we want to find the vector AB. See how could that help us? Well, the reason it's useful to find out what AB is because that will allow me to find out what OC is somehow. Or I could also find out the vector OB, which is opposite the CD, and then we could use the idea that this side is K times smaller than this side here. So if I find out what AB is, I can find out what OB is somehow, maybe. So let's find out the vector AB. So if I was to find out the vector AB, we are starting at A, we are finishing at B. So we could go A to O, O to D, and D to B. And so we have the vector AB equaling AO plus OD plus DB. So I've got the vector AO, which is negative P, the vector OD, which is Q, and the vector DB, we already know what that is. That's KOA, which is KP. So we add on KP. So now that we've done that, we have found the vector AB, which is equal to negative P plus Q plus KP. We can now find the vector BO, and we already know what CD is. CD is minus P plus 1 minus KQ. So let's find the vector BO. We are starting at B, we are finishing at O. So the vector BO is equal to BA plus AO. So BA, well, that's a negative of this vector here. So we've got the negative of the vector here, which is P minus Q minus KP. And then we add on AO, starting at A, finishing at O, that's negative P. And this will simplify to negative Q minus KP. So let's add this vector on. So instead of us finding OB, let's find the vector BO, which is equal to negative Q negative KP. Now, we already know what CD is. That's a fraction of K times the length of BO. Let's write that down. As KCD is equal to BO, we can therefore conclude that CD equals 1 over K times BO. So we have found the fraction of BO by dividing by K. Now, we already know what BO is. So we've got 1 over K, lots of minus Q minus KP. And if I multiply this out, we've got 1 over K times by minus KP, which is just minus P. And then we've got 1 over K Q. And that's exactly what we wanted to show. Now let's call this 2. And let's call that one 1. Now we've just found out what CD is. CD, starting at C, finishing at D, we've just found that to be minus P minus 1 over K Q. And so what we now need to do for part C then is find the value of K. And we can do that by comparing the Q components of equation 1 and 2. The reason for that, the p components are the same, and because they're the same vectors, the q components must also be equal. So then, for part C of the question, we compare the q component from equation 1 and 2. From equation 1, the q component, we've got 1 minus k, and this will equal the minus 1 over k. And then if I simplify, I've got k squared minus k minus 1 equals 0. Use the quadratic formula. K equals, well, I've got minus 1 plus minus 1 squared minus 4 times by 1 times minus 1 square rooted divided by 2 times by 1. So we have k equals 1 plus minus the square root of 5 divided by 2, and because k must be greater than 0, and the reason for that is the direction of dB would change because of that. So the arrow would go the other way in that case. So we can therefore conclude k equals here we've got negative 1 rather, 1 plus square root of 5 divided by 2 only. Now, for part D, by considering the triangle DBC, or otherwise, we have to find the exact value of the sine of 54 degrees. Now, we know already that regular pentagons have an interior angle of 108 degrees, and here's the calculation for that. So, we've got the 108 degrees over here, and each of those angles will be 108 degrees. Now, how does this help us? How does that relate to the 54 degrees in the question? Well, for that, recognizing that half of the 108 is 54, what we can do is essentially half this angle here, which means that this angle is 54. Now let's just draw that out neatly, and let's consider the triangle DBC with it. And if we do that as well, we also need to recognize that we'd have an isosceles triangle. So we've got DBC, and what I'm suggesting is we split that angle over here. So if I split this angle like so, then these two angles will be 54 degrees. Now, to find out what the angle here is, we've got angles in a triangle sum to 180. We've got an isosceles triangle because this side equals this side. So the angle here is 36 degrees. The angle here is also 36 degrees. Now, from this information, we can use regular trigonometry, recognizing that we have right angle triangles. And we want to find out what sine 54 is. Now, sine relates to the opposite and the hypotenuse. So, if we were to find out what sine 54 is, we've got the opposite. Now, what we've done here is we've split in half dB. So, we've got the opposite, which is 1/2 the vector dB. And then we take the magnitude of it, because we are just considering lengths. And then we divide this by the hypotenuse, which is what the vector CD is, as we see over here. Now, what is half of the vector dB? Well, we know the vector dB, going back to the question, is equal to k times the vector OA. So, what this is the same as is the magnitude of 1/2 k OA. And the magnitude of CD is also equal to OA. Now, why is that the case? Well, the reason this is replacing this is because we are considering magnitudes of vectors, so we're considering lengths, and each side of a regular pentagon is equal. And so with that, what we end up with is a 1/2 k. But we already know what k is. That is 1 plus the square root of 5/2. So we have 1/2 of the vector, rather 1/2 of the value k, so that's 1 plus square root 5/2, which is equal to 1 plus square root 5/4. So that is what sine 54 is equal to. Question number 4. A particle of weight W lies on a rough plane. The plane is inclined to the horizontal at an angle alpha, where tan alpha equals 3/4. Now, if that's the case, we can form a 3, 4, 5 triangle. Sin alpha is 0.6, cos alpha is 0.8, and tan alpha is 0.75. The coefficient of friction between the particle and the plane is 1/2. The particle is held in equilibrium by a force of magnitude 1.2 W. The force makes an angle theta with the plane, where theta is in between 0 and pi, and acts in a vertical plane containing a line of greatest slope of the plane, as we see in figure 2. For part A, we have to find the value of theta for which there is no frictional force acting on the plane. Now, what we need to do here is resolve parallel to the plane. So for part A, if we resolve parallel to the plane, then if I first of all draw the weight force acting downwards, here we've got W, and then the component of it, which is parallel, well, we've got this component over here, and that will equal this component over here. And the reason for that is we can think of it as going forward like that. So we want this component here, which is equal to this component here when in equilibrium. So we have 1.2 W cos theta, which is the external force here, and that will equal the component of the weight parallel to the plane, which is W sine alpha. And so, recognizing that sine alpha is 0.6, we've got 1.2 W cos theta equals 0.6 W. So cos theta is equal to 0.5, and therefore theta is equal to pi over 3. We need to be in radians. For part B of the question, the minimum value of theta for the particle to remain in equilibrium is beta. We have to show that beta equals the arc cosine of root 5 over 3 minus the arc tangent of 1/2. Well, for part B, we need to realise that as theta decreases, cos theta increases. Why are we considering that? Because we're looking at the component parallel to the plane. And so if that's the case, then the component of 1.2 W parallel to the plane will increase because cos theta is increasing. So there's more friction, there's more force pushing up the plane. And so what we can say from that then is the friction, FB, acts down the plane. So friction will act down the plane, and if I show that, here is our friction force, FB, acting down the plane, and the particle is moving up. Now, for this to remain in equilibrium, well, let's resolve parallel and perpendicular and then use limiting equilibrium, FB equals mu r. Now, if I resolve parallel to the plane, I've got 1.2 W cos beta minus the friction force FB equals W sine alpha. And that's resolving parallel. And if I were to resolve perpendicular to the plane, well, before we do that, let's simplify the result here. We can see then, if I rearrange for FB, FB is equal to 1.2 W cos beta minus 0.6, because that's what sine alpha is, W. And now if I resolve perpendicular to the plane, well, we've got a reaction force. We'll call this reaction force R. And that will equal the component over here, and if I extend this line over here, we've also got the component over here. If I've got the 1.2 W here, I've got this component, and I've also got this component. And so, if I were to resolve perpendicular to the plane, we have the reaction R equaling W cos alpha plus 1.2w sine beta. And therefore, r is equal to 0.8w, that's because cos alpha is 0.8, plus 1.2w sine beta. Now we are in limiting equilibrium, so we've got FB equals mu r. So we've got FB, which is this quantity here, and that's equal to 1/2 the coefficient of friction multiplied by r, which is this result here. And so, recognizing the w's cancel, we have 1.2 cos beta minus 0.6 equals 0.4, that's a half times 0.8, plus 0.6 sine beta. And so therefore we can see then 2 cos beta minus sine beta equals 5/3. Now what we'll do is we'll try to simplify the left hand side. So what we'll do here is we'll consider what's going on the left hand side, and on the left hand side we've got 2 cos beta minus sine beta, which in harmonic form is equivalent to r cos of beta plus some value gamma. And if I expand out, I've got r cos beta cos gamma minus r sine beta sine gamma. So comparing the cos betas, I've got 2 equals cos gamma, and if I consider the sine betas, then I've got 1 equals sine gamma, and from this we can conclude that tan gamma is equal to 1/2, from which we can see that gamma is equal to the inverse tangent of 1/2, and we can also conclude r is equal to 1 squared plus 2 squared all square rooted, which is square root 5. And so therefore, knowing what r is, we can rewrite the left hand side as root 5 multiplied by the cosine of beta plus gamma, which is the inverse tangent of 1/2, and this is equal to 5/3, and therefore you will find beta to equal the inverse cosine of root 5/3 minus the arctangent of 1/2. And that's exactly what we wanted to show. For part C of the question, we have to find the range of values for theta for which the particle remains in equilibrium with the frictional force acting up the plane. So here, we've got the frictional force acting up the plane. So this time, friction is acting up the plane. We'll call this force Fc. Now let's resolve. So if we, for part C, resolve parallel to the plane, this time we'd have Fc plus 1.2 W cos theta equaling W sine alpha. And we know what sine alpha is, that's 0.6. And so therefore, Fc is equal to 0.6 W minus 1.2 W cos theta. And exactly the same thing as we did in part B, we can find out what the reaction force R is. We've got 0.8 W plus 1.2 W sine theta. Now, if we consider limiting equilibrium this time, with friction acting up the plane, Fc equals mu R. We've got Fc, which is the 0.6 W minus the 1.2 W cos theta, and that's equal to 1/2 lots of R, which is 0.8 W plus 1.2 W sine theta. And if we attempt to tidy this up, W's cancel, so I'm left with 0.6 minus 1.2 cos theta equals 0.4 plus 0.6 W cancels, and then we've got the sine theta. And so if I rearrange, I have 2 cos theta plus sine theta equals 1/3. Now let's consider what we've got on the left hand side. So if I consider the left hand side, I've got 2 cos theta plus sine theta, which is equivalent to R times by the cosine of theta minus x. And so we've got R cos theta cos x plus R sine theta sine x being equal to this. And so comparing the sine thetas, rather compare the cos thetas, we've got 2 equals R cos x, and if I compare the sine thetas, I've got 1 equals sine x. And so therefore, at this point, we can see that tan x is equal to 1/2. So x is equal to the inverse tangent of 1/2. And knowing that, we can now, as we did before, find out what r is. R is equal to 1 squared plus 2 squared square rooted, which is square root 5. And so therefore, we know what r is, we know what x is. We can conclude over here, we've got the equation root 5 times by the cosine of theta minus the inverse tangent of 1/2 equals 1/3. And what we need to do is find out what theta is in this case. So theta is equal to the arc cosine, the inverse cosine of, well, here we've got root 5 over 15 minus, rather plus, the inverse tangent of 1/2. And so the range of values we have, we've got pi over 3, which is less than theta, which is less than the result over here. And the reason we don't include the equality here is because for pi over 3, that's when we've got no friction, and we need friction. So if we go back to the question, we were told in part C, we have a frictional force. So the range of values we have is shown over here. Question number 5. We have the graph of y equals tan squared x. We've got the graph of y equals 4 cos 2x. And we have to show that the area of the finite region between the curves y equals tan squared x and y equals 4 cos 2x minus 1 in the interval minus pi over 2 to pi over 2, shown shaded in figure 3, is given by 2 lots of the square root of 2 root 3 minus 2 lots of the square root of 2 root 3 minus 3. Now before we do anything else, we need to find out the intersection points of the graphs. So what we will do is we will set y equals tan squared x equal to 4 cos 2x minus 1. And so if I do that, I've got tan squared x equals 4 cos 2x minus 1. If I use the standard identity for tan squared, which is sec squared x minus 1, and if I use the standard identity for cos 2x, now because I've got a sec squared, which involves a cos, I'm going to replace the cos 2x with 2 cos squared x minus 1, and then I've got the extra minus 1 here. Now if I rewrite sec squared as 1 over cos squared, I've got 1 over cos squared, and then I've got the minus 1. This is equal to 8 cos squared x, and then I've got minus 4 minus 1, which is minus 5. And then if I multiply through by cos squared, I've got 1 minus cos squared x equals 8 cos 4x minus 5 cos squared x. And if I rearrange, I've got 8 cos 4x minus 4 cos squared x minus 1 equals 0. And if I attempt to find what the value of cos squared x is, well, here I need to use the quadratic formula. I'm going to have minus 4 plus minus 4 squared minus 4 AC square rooted divided by 2 times 8. And so if I tidy this up, what we'll be left with is cos squared equaling 1 plus square root 3 divided by 4 only. We can't take the negative because when I square root, can't square root a negative. Well, the way we'll approach this is to say the intersection point theta satisfies cos squared theta equals 1 plus root 3 over 4 only. And so what we can do at this point is find out the area. Now, what we'll do, if we're saying that the intersection point is theta, we're going to be taking the positive value of theta over here. And if we know what cos squared theta is, well, from here, we can conclude that cos theta is equal to the square root of this. So if I square root the 1/4, I get 1/2. So I end up with 1/2 times by 1 plus square root 3 all square rooted. So that's what cos theta is. And I can also find out what sine squared is. That's equal to 1 minus cos squared. So I've got 1 minus the 1 plus root 3 over 4, which is equal to 3 minus root 3 over 4. And if I square root, then sine theta is equal to 1/2 of the square root. So let's just write this down. We've got from here then sine theta equaling 1/2 multiplied by 1 plus, rather 1/2 multiplied by 3 minus square root 3 all square rooted. What we can also do is find out what tan squared is. That's equal to sine squared divided by cos squared. So I've got sine squared, which is this result here, divided by cos squared, which is 1 plus root 3 over 4. So tan squared is equal to 3 minus root 3 divided by 1 plus square root 3. And if I rationalize by multiplying through by 1 minus square root 3 on the top and bottom, then we can conclude tan squared is equal to 2 root 3 minus 3. And so therefore, tan theta is equal to 2 root 3 minus 3 square rooted. So now that we know all of these, what we can now do is find out the area. Now, because of symmetry, I will find out one of these areas and multiply it by 2. So if I were to find out the area, I've got 2 lots of the integral from 0 to theta of 4 cos 2x minus 1 minus tan squared x dx. And what this is equal to is the integral from 0 to theta of 4 cos 2x minus 1 minus sec squared x minus 1 dx. I'm finding out integrable values. And don't forget, I need to multiply this by 2. So I've got 2 lots of the integral from 0 to theta of 4 cos 2x, and then minus 1 and the plus 1 cancel out, and then I've got minus sec squared dx. And if I integrate, I've got 2 lots of, well, here, if I integrate 4 cos 2x, I end up with 2 sine 2x, and if I integrate minus sec squared, I've got minus tan x. So I need to evaluate this between 0 and theta. Now, before I substitute in theta, I can use a known identity for tan 2x. So I've got 2 multiplied by, well, here I've got 2 times by 2 sine x tan x, rather 2 sine x cos x, minus tan x. I'm evaluating this in between 0 and theta. So I end up with, well, if I bring the theta in, and recognizing that sine of 0 and tan of 0 are 0, what we are left with is 2 multiplied by 4 sine theta cos theta minus tan theta. And knowing that sine theta, cos theta and tan theta are what we worked out before, we can substitute all those values in. So I've got the 2 on the outside, and inside I've got 4 multiplied by, well here sine theta, that's the same as 1/2 multiplied by 3 minus square root 3 square rooted multiplied by 1/2 multiplied by 1 plus square root 3 square rooted, and then tan theta, that's the same as 2 root 3 minus 3 square rooted. And if I simplify this, well, 4 times a half times another half, that's just going to be 1. So I've got 2 multiplied by this result multiplied by this minus this. And let's see if I can simplify any of this. Well, I can simplify these two brackets. I would have 3 minus root 3 multiplied by 1 plus root 3, and then all of this is square rooted. Subtract this, and then here I've got 3, and then here I've got 3 root 3 minus root 3, and then I've got minus 3. So that simplifies to 2 root 3, all square rooted. So I've got 2 multiplied by 2 root 3 square rooted, subtract this here. And if I multiply the 2 into the bracket, I have 2 multiplied by 2 root 3 square rooted, subtract 2 multiplied by 2 root 3 minus 3 square rooted. And this is the required area. Question number 6. For the first part, Eden, who is confused about the laws of logarithm, states that log base 5 of p all squared equals log base 5 of p squared, and log base 5 of q minus p is equal to log base 5 of q minus log base 5 of p. However, there is a value of p and a value of q for which both statements are correct. Determine these values. Well, I'm going to call this first one equation 1 and the second equation 2. The first thing is to recognize we need to solve these simultaneously to find the values of p and q. So if I take a look at equation 1, then I've got log base 5 of p squared equals, now here I'm going to use the power law of logs, so that I've got 2 multiplied by log base 5 of p. And if I rearrange, I've got log base 5 of p squared minus 2 multiplied by log base 5 of p equals 0. Let's now factorize. So I've got log base 5 of p multiplied by log base 5 of p minus 2 equals 0. So either log base 5 of p equals 0, or we've got log base 5 of p equals 2, and from which we can see p is either equal to 1, that's 5 to the power of 0 equals p, or we've got p equals 5 squared, which is 25. Now, if we take a look at equation 2, we can simplify the left-hand side. So from equation 2, the left-hand side will remain the same as log base 5 of q minus p, but the right-hand side, we can use the subtraction law of logs. So I've got log base 5 of q over p. That's just using the subtraction law of logs. And if I anti-log both sides, we end up with q minus p equals q over p. And with these values of p, we can find the value of q. So when p equals 1, I've got q minus 1 equals q over 1. Well, here we've got no solutions. So here we have no solutions. However, when p equals 25, I've got q minus 25 equals q over 25. And from this, we can see that q is equal to 24 over 625. So there is only one set of values of p and q which satisfies this. We've got p equals 25 and q equals 24 over 625 only. For the next part of the question, we have to let r equal a positive real number where r doesn't equal 1, and we have to prove that log base r of a equals log base r squared of b implies a squared equals b. So, for the next part of the question, we have log base r of a equals log base r squared of b. Now if I have r squared to the power of this equaling r squared to the power of this, what we are essentially doing is anti-logging both sides. And so, using the laws of indices on the left, we've got r to the power of 2 log base r of a equaling, now here we end up with just b. Now using the power law, I've got r to the power of log base r of a squared equals b. So I'm left with a squared equals b. And that's exactly the result I wanted to show. Now we have to solve log base 4 of 3x squared plus 26x squared plus 40x equals 2 plus log base 2 of x plus 2. Now, first of all, we've got log base 4 of 3x cubed plus 26x squared plus 40x equals 2 plus log base 2 of x plus 2. Now, here we are given a clue. We've got a base of r here and a base of r squared. You'll notice r squared, 2 squared is 4. So we can use this idea to help us solve this equation when we've got different bases. Now, before we do anything else, the left-hand side remains the same. However, on the right-hand side, I can rewrite 2 as log base 2 of 4. So 2 is the same as log base 2 of 4. I'm just combining the logs. And then I add on log base 2 of x plus 2. So, on the right hand side, we can combine the logs. So, we have log base 2 of 4 multiplied by x plus 2. And now if we do 4 to the power of what's on the left and what's on the right, so we've got 4 to the power of this equaling 4 to the power of this. We need to now simplify all of this. Well, first of all, on the left hand side, 4 to the power of log base 4 of something will just equal that something. So on the left hand side, we've got the result shown here. But on the right hand side, 4 we can rewrite as 2 squared. So we've got 2 squared to the power of this. And if I use the laws of indices, the left hand side remains the same, but on the right hand side, I've got 2 to the power of 2 times by the log base 2 of 4 lots of x plus 2. And if I power slide this 2, again, left hand side remains the same, but on the right hand side, I've got 2 to the power of log base 2 of 4 lots of x plus 2 squared. So what will I end up with? I've got 3x cubed plus 26x squared plus 40x. The left remains the same, but on the right, I've got 4 multiplied by x plus 2 all squared. So 4 to the power of 2 is 16, and then I've got x plus 2 all squared. Now on the left, I can factorize out an x, so I've got x multiplied by 3x squared plus 26x plus 40. And on the right, I still have 16 multiplied by x plus 2 all squared. Now, I can factorize the left as x multiplied by 3x plus 20 multiplied by x plus 2, and this will equal the result shown here. And so if I take everything over to one side and then subtract 16 multiplied by x plus 2 all squared, the result of this is 0. Now if I factorize out an x plus 2, then I've got x plus 2 multiplied by x lots of 3x plus 20, and then I've got minus 16 lots of x plus 2, and all of this is equal to 0. So now let's tidy up the bracket. I've got x plus 2, and then here I've got 3x squared plus 20x minus 16x plus minus 32 equal 0. So I have x plus 2 multiplied by 3x squared plus 4x minus 32 equals 0. Can factorize again. So I've got 3x squared plus 4x minus 32, which can be rewritten as 3x minus 8 multiplied by x plus 4. And then I've still got the x plus 2. This is all equal to 0. So from here you can see we've got x is minus 2, 8 over 3, or minus 4. But the equation is not defined for negative numbers. So it's not defined for x equals minus 2 or minus 4. And from this we can conclude x equals 8 over 3 is the only solution. Question number 7. A circular tower of radius 1 meter stands in a horizontal field of grass. A goat is attached to one end of a rope. At the other end of the rope is attached to a fixed point O. At the base of the tower, the goat cannot enter the tower. And taking the point O as the origin, the center of the base of the tower is at the point 0, 1, that's the coordinates of t, where the unit of length is 1 meter. The rope has length pi meters, and you may ignore the size of the goat. The curve C shown in figure 4 represents the edge of the region that the goat can reach. For part A, we have to write down the equation for C for y being less than 0. Now, we've got this rope over here, okay, and this rope, what's happening is the goat can move around. We know the rope has a length of pi, so here the radius will be pi of this bit of our circle. Of course, there we've got a semicircle. And so, for part A, recognizing that it passes through the origin, our equation is x squared plus y squared equals pi squared. Now, part B of the question. When the goat is at the point G with coordinates x, y, with x being greater than 0 and y being greater than 0, as we see in figure 4, the rope lies along OAG, that's basically this bit over here, where OA is an arc of the circle with angle OTA equaling theta radians, and AG is a tangent to the circle at A. With the aid of a suitable diagram, we have to show that x equals sine theta plus pi minus theta lots of cos theta, and y equals 1 minus cos theta plus pi minus theta lots of sine theta. Now here is the enlarged circle, rather the enlarged diagram. So how could I find out what OA is? Well, OA is a rectangle. Rather, it's an arc. So OA is equal to pi, rather OA is equal to radius, which is 1, times by the angle theta. So OA has a length of theta radians, and AG, if the length of the entire rope over here is pi, then we take away this little bit, leaving us with this bit over here. So AG has a length of pi minus theta. And what we need to do is find out the coordinates of x and y. Now, the way we'll do this is, if we let x be the point vertically below g such that gx here is 90 degrees, in other words, we've got this situation, then how could we find out what the x coordinate and the y coordinate of g are? Well, this angle here will be theta, and the way we can figure that out, if I extend this line and have this here and then extend that down, that's going to be theta. This is going to be 90 minus theta, and then recognizing that this and this are perpendicular, this angle here is going to be theta, and here we're going to have 90 minus theta. So that's where we can figure all that out. So we've got that angle equaling theta, and so for us to find out what x is, we've got, well, how many are we going across? We've got this component over here going across, and that will equal, well, if the circle has a radius of 1, then we've got 1 sine theta, which is just sine theta, and then we need to add on this bit over here, which is GA cos theta. Okay. Now, do we know what GA is? We've already worked out, that's pi minus theta. So I've got sine theta plus pi minus theta multiplied by cos theta. And if I consider what the y coordinate of G will be, well, the way we will approach this is, well, here we'd have this length here, x, G, which is GA sine theta, but we also need to add on this tiny length over here. Now, the way we'll approach this, here we've also got 1, and we need to take away this bit over here. Now this blue length, we've got 1 cos theta, and so this bit over here is going to be the 1 minus the 1 cos theta. So we add on then 1 minus cos theta. And what we can also do is find out what we can substitute in GA. So I'm left with 1 minus cos theta plus GA sine theta, so I add on pi minus theta sine theta, and that's exactly what we wanted to show. So here as well, I've got the pi minus theta, which is the length AG. For part C of the question, by considering the integral of y multiplied by dx over d theta, we have to show that the area in the first quadrant between C, the positive x-axis and the positive y-axis, can be expressed in the form the integral from 0 to pi of u sine u du plus integral from 0 to pi of u squared sine squared u du plus integral from 0 to pi u sine u cos u du. So what area is this looking for? Well, the area we're looking for is this area here. We need to find the area of that. So how could I do that? Well, before we do anything else, if we go back to the formula, we need to work out what dx over d theta is. So I know what x is. I need to work out what dx over d theta is, and I can do that using the product rule. So dx over d theta, that will equal, well here if I differentiate cos, if I differentiate sine I get cos, and using the product rule I've got here the differential of pi minus theta, which is minus 1, multiplied by cos theta, and then we've got the differential of cos theta, which is minus sine, and then multiply that by pi minus theta, and cos theta minus cos theta simplifies to 0, so we are left with minus pi minus theta sine theta. So that's what dx over d theta is. So what's the area going to equal? Well, the area that will equal, well, we're integrating. What are our limits going to be? Well, we're going to start off at x equals 0, and theta is varying, so theta starts, so this line starts off over here, and then as theta varies, we go up to here as theta varies. So the area, we're going from x equals 0 to x equals pi, and that's because in Cartesian form we are at 0 here, and then we go to pi, and then we've got y, the function y, which is, well, let's just open up brackets. We've got our function y, which is this over here, and then we've got to multiply this by this, which is dx over d theta, and then I've got d theta. So this is what I need to work out. So if I'm integrating between, with my variable being theta, that means I'm going to go from pi to 0 of this result here. So now what we can do is, if I go back to the show that, here we've got things involving u's. So I need to make a suitable substitution. So if I let u equal pi minus theta, then du divided by d theta equals minus 1, and therefore du equals negative d theta. In other words, negative du equals d theta. And when theta equals pi, u is equal to pi minus pi, which is 0, so this is our lower limit. And when theta equals 0, u equals pi minus 0, which is pi. This is our upper limit. What we can also do is recognize that the cosine of pi minus theta is the same as minus cos theta, and the sine of pi minus theta is the same as sine theta. So now we can find out what our area will equal. So therefore, for the area, what will we have? Well, I've got the integral from 0 to pi, and if I take the minus from here, because I've factored out a minus, then inside the bracket, what will I have? Well, I've got the 1, and here I've got minus cos theta, but minus cos theta is the same as cos of pi minus theta, and then I've got plus pi minus theta, so that's plus u, multiplied by sine theta. Now sine theta is the same as sine of pi minus theta, so that's one bracket. And for the other bracket, what do we have? We've got minus u multiplied by sine of theta, which is the same as the sine of pi minus theta, and I've got the du at the end. So, replacing the pi minus theta with u's as necessary, some of them have already been done. We have minus the integral from 0 to pi of 1 plus cos of u plus u sine u multiplied by minus u sine of u du. And if I multiply all of this out, taking out the negative with this negative, we're going to be left with a positive. So I've got the integral from 0 to pi. Now here I've got 1 times by u sine u, so that's just going to be u sine u. And then here I've got cos u times by u sine u, so that's going to be u sine u cos u. And then here I've got u sine u times by u sine u, so that's going to be u squared sine squared u du. So now I need to simplify all of this even further. So I've got the integral from 0 to pi of u sine u du plus the integral from 0 to pi of u squared sine squared u du plus the integral from 0 to pi of u sine u cos u du. So let's just move all this over here. And that's exactly what I wanted to show. Now we have to show that the integral from 0 to pi of u squared sine squared u du is equal to pi cubed over 6 plus the integral from 0 to pi of u sine u cos u du. So for part D, we've got to work out the integral from 0 to pi of u squared sine squared u du. And to do this, I'm going to be using integration by parts. But before that, I can replace the sine u with something appropriate. I can replace the sine squared u with 1 minus cos 2u over 2. So I've got this integral from 0 to pi of this. So can we split this up? Well, I can split this up as the integral from 0 to pi of u squared over 2 subtract u squared cos 2u over 2 du. And splitting this up even further as two separate integrals, I've got the integral from 0 to pi of 1/2 u squared du subtract the integral from 0 to pi of 1/2 u squared cos 2u du. And now we need to integrate by parts. So what we will do now is consider the integral from 0 to pi of 1/2 u squared cos 2u du. So if I was to integrate this by parts, we've got 1/2 u squared multiplied by the integral of cos 2u, which is 1/2 sine 2u, and I need to integrate this between 0 and pi. I need to evaluate that between 0 and pi, and then I subtract the integral from 0 to pi of the differential of 1/2 u squared, which is u, multiplied by the integral of cos 2u, which is 1/2 sine 2u. So this is what I need to work out. And if I work this out, well, here, if I substitute in my upper and lower limits, recognizing that I've got sine of 2 pi, well, I'll write it out in full. We've got 1/2 pi squared multiplied by 1/2 sine of 2 pi, and then my lower limit will be 0 because I've got 0 squared, which is just 0. And then here I've got the integral of from 0 to pi of 1/2 u sine 2u du. And recognizing that this is 0, I'm going to end up with minus the integral from 0 to pi of 1/2 u sine 2u du. So how does that help me? Well, I can say then that the integral from 0 to pi of u squared sine squared u du, well, I know that's equal to the integral of from 0 to pi of 1/2 u squared du, subtract this result here, and so what we will be left with is the following. Well, if I integrate 1/2 u squared, I end up with a 6th u cubed. So I've got a 6th u cubed, which I need to evaluate between 0 and pi. And then the minus and the minus give a plus. Then I've got the integral from 0 to pi. And then here, I'm integrating 1/2 u sine 2u du. Now, here, I'm going to end up with pi cubed divided by 6. And then if I integrate 1/2 u sine 2u du between 0 and pi, again, I need to use, well, no need to use anything, because if I go back to my show that result is the same as what we've got here, u sine u cos u du. So I don't actually need to work that out. So here, I've got the integral from 0 to pi of 1/2 u. Now, sine 2u, that's the same as 2 sine u cos u du. Now the half and the 2 cancel, so I'm left with pi cubed over 6 plus the integral from 0 to pi of u sine u cos u du. So that's what we end up with. And that's exactly what I wanted to show. Now, for part A, hence find the area of the grass that can be reached by the goat. Now, let's first of all find out this red area. For us to do that, we need to find out some values. Let's integrate the u sine u du between 0 and pi. If we were to consider the integral from 0 to pi of u sine u du, we can find out what this is by integration by parts. So I've got u multiplied by the derivative of sine, rather the integral of sine, which is minus cos, in between 0 and pi, and then I subtract the integral of sine, which is minus cos. So that will give us minus cos u, and then I multiply that by the derivative of u, which is just 1. And I'm integrating this between 0 and pi. So I've got minus u cos u evaluated between 0 and pi plus the integral from 0 to pi of cos u du. Now if I substitute in pi, what I'm going to end up with is minus pi times by the cosine of pi, and then my lower limit will just be 0 because I've got 0 for u. And then the integral of cos is positive sine. So I add on sine u, and I'm going to evaluate this between 0 and pi. So I've got minus pi cos of pi plus sine of pi. Now sine of 0 is just 0, and sine of pi is 0. So I've got minus pi times by cos of pi, which is minus 1. So I'm left with pi for that integral. Now let's consider this integral here. So now if we consider the integral from 0 to pi of u sine u cos u du, I've got the integral from 0 to pi of u multiplied by sine 2u multiplied by half sine 2u is sine u cos u. And what we need to do now is work out what this is. So to work out what this is, I can use integration by parts once again. So we have the differential of u, which is 1. Rather, here we've got a half u multiplied by, well, here, integrating sine 2u, I end up with minus a quarter cos 2u in between 0 and pi. And then I add on then I've got minus the integral of, here I've got u dash, which is 1, times by the integral of a half sine 2u, which is minus cos 2u over 4 du. And I'm evaluating this between 0 and pi. So I have here minus here, this result here is 1/2. And the reason it's 1/2 is because I'm integrating sine 2u. And I've already got the half there. So what we can now do is find out the value of this. So if I substitute in for my upper limit, well, here I'm going to have a minus pi over 4 times by the cos of 2 pi, and then here I'm adding on the integral from 0 to pi, the integral of 1/4 cos 2u du. Now cos of 2 pi is 1, so here I'm left with minus pi over 4, and then here, integrating 1/4 cos 2u, what we will end up with is 1/8 sine 2u in between 0 and pi. So if I substitute in for my limits, I'm going to have minus pi over 4 plus 1/8 sine 2 pi. Now sine of 2 pi is just 0. So I'm going to be left with minus pi over 4. Okay. So how does this help us? Well, we still need to find the area which is shown in red over here. So how could we work out that area? Well, that area which was shaded, that is given by the integral which we wanted to show, which was over here. That's the result we wanted to show. Now, u sine u integrated, we worked that out before here. We got a value of pi. And then this value here, we worked out in over here. We got pi cubed over 6. So here I'll just write it as a 1/6 pi cubed, and then we added on, if you remember, u sine u cos u. So we added on the integral from 0 to pi of u sine u cos u du in between 0 and pi. So that was this here. And then we're adding on to it this result here. So what will we be left with? Well, we've got pi plus a 1/6 pi cubed plus 2 lots of the integral from 0 to pi of this. Now, this bit here, we already worked out the integral of u sine u cos u. We worked that out to be minus pi over 4. So, we have pi plus a 1/6 pi cubed plus 2 lots of minus 1/4 pi. And so what we are left with for that area is a value of a 1/6 pi cubed plus 1/2 pi meter squared. So, now that we've done that, what other areas do we need? Well, we need the area of the semicircle. So if I go back to my diagram in the question, so we need the area of that semicircle. So the area of the semicircle, we've got a 1/2 pi times by the radius, pi squared. Remember, the radius is pi. And so here, the area of the semicircle is 1/3 pi cubed. Rather, it's equal to 1/2 pi cubed. Now, we also need to work out the area of the base of the tower as well. So, the area of the base of the tower that will equal pi times by 1 squared. The radius of that is 1 meter. So here I just end up with pi meter squared. And so the area of the grass, which is what we need, the area of the grass reached by the goat, well, here, first of all, we've got the area of the semicircle, which was a half pi cubed. Then we've got the area of the base of the tower, which was pi. We've got two lots of this result here. Okay. And the reason we've got two lots of that is because if we go back to our original diagram, we'd also have the repeat of this on the other side, and that's through symmetry. So that's why we multiply that by 2. And then we add on the area of the semicircle. The area of the semicircle is the 1/2 pi cubed. And then we subtract the area of the base of the tower, which is pi. So now we need to tidy all of this up. We've got pi minus pi, which is 0 pi. And then I've got 2 times by a sixth, which is a third. So I've got a third pi cubed plus a half pi cubed. And it turns out the area we require is 5/6 pi cubed meter squared as the area of the grass reached by the goat.